Okay, charging discharging curves for an inductor. If you have looked at the capacitor, charging discharging curves, these are going to be fairly familiar. The circuit will start with charging curves. We just go to EMF, resistance. It may not even be a resistance separate from the inductor. The inductor has its own resistance, and we can model that in series with the coil. So we turn the whole swing on, didn't put a switch, but once this gets turned on and connected, current flows. You all know that situation, and it tries to build up very quickly. That means there's a magnetic field building up quickly inside the coil. That means there's a flux building up quickly. The inductor is going to try and resist this, and it's obviously going to produce a voltage like that to try and oppose it. And so we can actually write this as a Kirchhoff's equation, and we do it the normal way, which is E minus, we've got a current, we'll call it I, that resistance in that one. We can include the little resistance that's in the coil, so IR, and then we've got the voltage in the coil, which is, hopefully you've learned using the inductor formula, that's L di dt, and that's all got to equal 0, right? Now the thing is, you might be going, there was a negative on the L di dt, and so maybe that would be a plus there, or a positive. But remember that the whole point of the negative was to show that this was around the opposite way from the supply. So if we look at it from that point of view, and we just forget about, we know that L di dt is the actual value of the voltage, we could just look at it and get the direction from our Kirchhoffs. If we come out of a positive in our Kirchhoffs, we make it a positive, and if we come out of a negative, we make it a negative. So we can write that as negative, not a negative equaling a positive. So once we do all that and solve that differential equation, not too tricky to solve, separation of variables, all that sort of thing, we're going to get a graph that looks like that. I is a function of t and t. Now this is the one that we know is the 0.631, and once we know that one, we know the other curves. If we want the equation, which is the whole point of doing this, discharging curves and formulae, then we know this is going to be one of those 1 minus E1s. It's going to finish up being at a current which is just going to be equal to the resistance, or the voltage divided by the resistance. So the voltage in this one, E divided by R, and if we'd solved the equation, we would have got the time constant like that. So this is I as a function of t equals that. Alright, and we have seen with our capacitor curves where the 0.63 comes from. It's just e to the minus t over the time constant. When the time equals the time constant, it's minus 1, which is 1 over e, which is 1 over 2.7, which equals 0.37. 1 minus 0.37 equals 0.63. So that's the curve for the current charging. Alright, now the discharge curve, if one thing that I've said to you in the past is that if you can remember the capacitor charging curve, which just looks like this one, but it's voltage against time, you'll know how all the other curves look, because the inductor one the curve that's like that will be the current against time. All the other curves, the 3 for inductor and 3 for capacitor, will look like that. That's the 0.37 curve. So we know the formula. This is voltage against time. Voltage, this is voltage in the inductor, not the supply. Starts off high and goes low. So it's going to start off at the value of the we want to know the voltage across the inductor as a function of time is going to be equal to E times e to the minus t over tau. Alright, starts off high, gets less. When it equals 1 time constant, it's 0.37. 2 time constants, e times 0.37 squared. So if you want to know how we get a bigger voltage in that when we discharge it, I've done another little video on that, but let's just present the discharge curves. The current against time and the voltage against time, or current against time, we said all the others are going to look like that. So this one's going to start off at the maximum current, which I think we just said. Did we put it on our little graph here? maximum is just E over R, so it's going to start off at E over R and then decrease. So our formula for the discharge, just write that on here, discharging I against T is just going to be equal to E over R, E to the minus T over time constant, right? So the voltage discharge curve, same, it's going to start off at E, so voltage against time is just going to be equal to E to the minus T all over the time constant. So there's the formulas for the graphs, which you will need to do slightly trickier problems when you want to use the logs. What else did I want to say? The voltage against time, really, this little guy for the charging, we could have said that it actually should have looked like that with a negative voltage, because it's round the other way from the supply voltage. So if we've actually said that the voltage of the supply is positive, then that one should be opposite. But we normally see it written like that, so I don't want to, I just want to draw your attention to that, and I don't want it to be confusing. All right.